Welcome back to day 3 of Engineering Training Days. I'm EE World Editor Martin Rowe, and today, at this session, we will have this virtual event will be available online and on demand at eetrainingdays.com, and these slides are available for you now through the resource widget. We will have a Q&A at the end, and if you're watching on demand, you will still be able to ask questions using the Q&A, and we will be able to respond to you. And remember to tweet us at hashtag EETrainingDays. EE World is the parent site of several websites dedicated to different topics for electrical engineers. They include 5G Technology World, Analog IC Tips, Sensor Tips, and Test and Measurement Tips. We have 2 other sessions coming after this one today. The first one will be at 2:30 Eastern Time, and it is From Design to Real RF Device Connecting EDA Simulation and Hardware Test. At 3:45 Eastern Time, we will have Designing RF and EMI Shielding for Manufacturability. And we would like to thank our sponsor, Anritsu, for this session. And now I'm going to turn this over to Philip Belleau, who is going to give us the presentation. Philip is going to start right now.
Thank you very much, Martin. Thank you very much, Martin. And thank you for all of those that are joining this webinar. I know you have busy schedules and you're taking time out of your day for this, but I'm quite certain there's a lot of great information in here. And without any further delay, let's get started. But I just want to talk a little bit about myself. I'm a senior product manager at the moment with Anritsu company in Morgan Hill, California. I've been with Anritsu for a little over 22 years. Half of that time was up in the Great White North, known as Canada. The other half has been here in sunny Morgan Hill, California. So let's move on. So the webinar, of course, is titled The Impact of Measurement Accuracy When Adding Coaxial Adapters After Calibration. And we're going to cover a bunch of things in here. And the first thing we're going to cover is who's the primary audience for this particular presentation. The reason why I'm covering this first is because it may not be applicable to everybody that's signed up for it. And I will understand if you don't stay through the whole webinar, but I can assure you that this presentation will have valuable information for anybody that wants to stay through the whole thing. We'll do a basic overview of what a modern cable antenna analyzer actually is. It may not be apparent to some people. We'll talk about the most common configuration for calibration antenna analyzer kits. We'll talk about calibration and why is it needed. Sometimes that's not clearly understood by some people. And then here comes the problem. You get to a site, but the connector is different on the device you need to measure. And what do you do now? You're going to use an adapter to connect to that device under test, but that adapter will end up, becoming part of the overall measurement. We'll discuss that in better detail during the presentation. And then, of course, we're going to talk about why should your adapter quality be a priority. And we'll have some examples of the types of specifications for adapters that you should avoid using or purchasing. We'll have plenty of real measurement examples. And for me, this is the meat on the bone. So, this is where you're actually going to see the difference between a good quality adapter and a, bargain adapter that you can buy on several online websites. And we'll talk about how to test the adapter, because if you really don't know how good your adapter is, if you can't test it, then you don't know if it's a good quality adapter, and you might get caught out in the field with a problem. And we'll talk a little bit about why a good adapter can sometimes go bad. And then we'll have wrap up and some questions. So the primary target audience for this is really the mobile network operator technicians and the cellular contractors, the people that are responsible for installation and maintenance of base stations and DAS systems. But again, as I mentioned earlier, all of the principles in here are fully applicable to different industries. And it's, as you go higher in frequency, let's say you're working in a lab with benchtop vector network analyzers and you're working at 40 gigahertz or 60 gigahertz or higher, these principles actually are more important at the higher frequencies. But you'll see how it impacts even at cellular frequencies. There's quite an impact when you have a poor quality adapter. So let's talk about this for a second. So it may not be apparent to some people, but a modern cable and antenna analyzer is really a vector network analyzer. It's a one-port vector network analyzer that uses vector error correction. That's what the calibration is. And it makes an S11 reflection-based S parameter measurement. Now, we generate or we create this GUI on these products that simplifies the use for the field technician, and we'll talk a little bit about that. This is basically, I just kind of jumped ahead. So as we go a little slower, I think the next slide will make this a little bit clearer, but you look at a benchtop vector network analyzer and you're going to see S parameter measurement capabilities and different log graph types. You look at a cable antenna analyzer and you're going to see a return loss measurement or whatever. So they both are capable of doing the same thing. It's just how the GUI presents it to the user. So the cellular industry and other industries as well, they have method of procedures, we call them MOPs. And those MOPs are written typically around cable antenna analyzers, especially for the cellular industry. So the measurements in the MOP are going to be return loss, cable loss, insertion loss, if it's a fault or whatever. And those are the types of measurements that the field technicians need to make. So this is where the differences between a cable antenna analyzer and a vector network analyzer start coming into play in terms of the ease of use for the product. VNAs measure S parameters. So for a field technician who's reading a MOP, and the MOP says, you know, measure return loss, and if that person's got a vector network analyzer, he's like, where's return loss? I don't see that measurement on this instrument. So you need to be able to understand what the equivalent of return loss is. And in the next slide or two, we'll talk about that. So this is the slide that I was talking about. I don't know if you see the mouse moving when I move the mouse. I'm not sure if that's available or not on the webinar. But basically, the MOP will have a procedure in it, and it's going to say, you know, measure return loss. And so what you're going to want to do is on your instrument, you want to see return loss. And so on a cable antenna analyzer, you're going to see return loss as an available measurement on the GUI for a cable antenna analyzer. But on a vector network analyzer, you're going to have to set S11 with a log magnitude graph, which will give you a dB response. And that's essentially the equivalent of return loss, with one exception. Sometimes a cable antenna analyzer return loss will be displayed as a positive number because the name return loss by definition is loss. So if it's a positive loss, that means it's a negative value from the point of a vector network analyzer. So the vector network analyzer will give you a 0 dB response at the top, and as it goes down, those numbers will be negative. On most cable antenna analyzers, it will be a positive number. The main thing to keep into play here is that it's the number that's the more important thing, not so much the sign for the cable antenna analyzer. Cable loss is another measurement that's defined in a MOP. And on the cable antenna analyzer, naturally, you're going to have cable loss as an available measurement type. But on a vector network analyzer, it's going to be the same S11 with log magnitude, but in this case, we have to divide the results by 2, and that's essentially the equivalent of cable loss. The next measurement you're going to have is distance to fault, and typically for the cellular industry, it's in the dB scale. So on your cable antenna analyzer, you're going to have distance to fault in a dB scale, or sometimes they'll call it distance to fault return loss. It's basically the same thing. There is also distance to fault as a VSWR measurement. Those are available as well. But again, the cellular industry tends to lean towards return loss. On a vector network analyzer, it's distance domain with a log magnitude graph. So you have to change the domain from a frequency domain to a distance domain and set the graph type correctly. But then there's another catch. The cable antenna analyzers have built-in cable lists And the typical cable list is going to have, the more common cables that are used out in the field. I think our site masters have like 237 cables built in. So when you're doing distance fault, you need to select the cable from the cable list, and then the cable loss factor and the propagation velocity factors of the cable get applied to that distance default measurement so that it gives you an accurate distance and it gives you an accurate amplitude. Vector network analyzers, most of them don't actually have this. So in that case, you're going to have a bit of a challenge getting more accurate results with the vector network analyzer. Both types of instruments have the ability for the user to do a manual setting for cable loss and propagation velocity, but it's a 1-point cable loss and it's a 1-point propagation velocity, so it's not quite as good as being able to use the list. And here's, some typical cable antenna analyzers from different manufacturers. There's several other types that are out here. I just decided to pick these few just to show. We've got some from Roden Schwartz and Viavi and Anritsu and Divisor, and there's countless other brands out there. But these are the ones that are, I would say, more valid cable antenna analyzers for the industry. And the common configurations. So these cable antenna analyzers will typically come with an N-type connector on them. So when they have the N-type connectors, they'll generally equip those kits with N-type calibration kits, which is fine until you run into the situation when you're in the field that the device you're testing isn't N-type, but that's what we're going to talk about later. And just going back, if you remember the picture of those cable antenna analyzers, I'll just show that picture really quickly here. These cable antenna analyzers, with the exception of the little guy on the bottom, you can't take that cable antenna analyzer and connect it directly to your device under test. So that's where you end up running into this issue where you have to use a test port cable. And you'll want to use a flexible phase stable test port cable because any movement of that cable will vary the phase, which is going to have some impact on the results. But once you've put that phase stable cable on, then you'll need to do a calibration at the end of that cable. We'll talk about calibration a little bit later on in the presentation. So calibration, why is it needed? Calibration corrects for the system errors, and the system errors are, instrument system errors as well as errors caused by anything that you've added to the test port. So that phase stable cable adds system errors. The instrument itself has system errors, so these errors are like frequency response, the amplitude response, and several other different factors go into this. The analyzer itself doesn't really know what a true 50 ohm impedance looks like, because it needs to have this calibration. And there's a slide coming up that I'll give you an analogy that might help some people to understand a little bit better the process of calibration or how it makes this handheld cable antenna analyzer measure 50 ohms much more accurately. So we talked about the phase stable cable. And again, if you have to use one, which you have to do with the more traditional type cable antenna analyzers, then you absolutely have to do a calibration at the end of that cable. So the main errors that are corrected, you have a directivity error, reflection tracking error, and a source match error. I'm not going to go into great detail on that, but those are basically the three, and those get corrected when you do an open short load calibration at the end of the test port or directly on the connector of the instrument, depending on what type of cable antenna analyzer you actually have. Some cable antenna analyzers actually have a permanent factory calibration applied to the connector. So basically, during manufacturing, they manufactured the instrument, they run it through all the manufacturing tests, and then they will do an open short load calibration, a very high quality open short load calibration actually. And then that calibration correction factor data will get stored in an internal memory. It usually goes into an EEPROM, and it stays there permanently in that instrument. And as long as you can make a direct connection from that connector to the device that you're testing, then you don't have to do an open short load calibration in the field. You get excellent results because you're relying on that factory calibration that's already been done. Now, when you get to the more classic style of cable antenna analyzers, like the larger ones in the previous picture, factory cal at those test ports is almost meaningless because you can't take that test port and connect it directly to the device that you're trying to measure. So I mean, it's all fine and good that there's a factory calibration there, but the minute you put that test port cable on, you've kind of lost your factory calibration. So you'll have to do an open short load calibration at that point. So this is an analogy, and I hope that it makes sense for some people. I wear glasses, as you can probably see in the screen. And if I don't have my glasses on, I can't really see what I'm looking at very well. It's not clear. And it's the same with the cable and antenna analyzer or vector network analyzer. It's trying to measure a 50 ohm impedance, but it doesn't have a clear view of that 50 ohm impedance. So you perform a calibration, and then suddenly you have a nice crystal clear view. You know exactly what 50 ohms is supposed to look like. So that's the real reason why you want to do a calibration. And then, of course, there's other reasons. Like I said, if you've added a phase-stable cable to the end of the analyzer, or if you've added some adapters or whatever, in a perfect world, you want to do a calibration afterwards. So now you're at the site, and your kit is equipped with N, and the connector's not N. So what can you do? In that perfect world, you would have adapters to adapt from the N type to whatever the type of connector your device under test has. And then you would also have the correct type of calibration kit to match the device under test. And then you would do a new calibration at the end of the adapter after you've added it. That's in the perfect world. There are some drawbacks. That means you would have to have a lot of different types of connectors. But more importantly, you would also have to have a calibration kit for each one of the different types of potential devices under test that you might have to measure. And that can quickly add up to some pretty significant expense. Then, of course, when new connectors come out, and there are new connectors being developed all the time, the industry that creates or provides calibration kits, the companies that provide the calibration kits to the industry may not actually have their calibration kits available to the public yet. So, you know, the connectors come out, and one of the perfect examples that I'll talk about a little bit is when the 4310 connector started becoming popular. There were plenty of 4310 connectors being installed on the new remote radio heads because they're smaller size, they're excellent pin performance, you know, so they got increased port density without having to have a massive size radio or a massive size antenna. But in the early days, there were no calibration kits. What there was adapters were the first things that come out, and that's typically what happens. The adapters to go from N or from some device connector type to another device connector type are usually the first things that hit the market. And then sometime later, the companies that make calibration kits will follow up and add calibration kits. The reason for this actually is certain connectors get developed, and there's some, let's say, anticipation that that connector is going to become the next big thing. And so that doesn't always happen. So there have been connectors historically that were developed because people thought that that was going to be the next best thing, or, you know, the next best slice gravy or sliced bread. And lo and behold, the industry just didn't adopt that adapter. So the companies that are doing, you know, products that support those types of connectors, like these calibration kits, they tend to wait a little bit to see how well these adapters get adopted by the industry. And if they get adopted really well by the industry, then you can bet that there will be calibration kits available for those adapters. I think there's a new adapter that's starting to be developed. It's a 2.23 something. It's roughly half the size of a 4310. And today, I can almost guarantee you there are no calibration kits in that format. So anyway, we use the adapter, and basically we'll now be able to connect to the device under test. So this is what I was talking about, where the industry may not be up to speed in terms of the calibration kits to support the new adapters or the new types of connectors. So in those cases, you're forced to use the adapter, but now you can't do that calibration at the end. So you've deviated from that perfect world where normally you would put the adapter on, you would then do the calibration at the end of the adapter, and you would get absolutely perfect results. If you don't have a calibration kit because the companies that build them haven't actually created them yet, you're literally forced to just use the adapter and hope for the best. So this is where the adapter quality is going to come into play, because if that adapter you bought happens to be a, poor quality adapter, you're going to have some issues. And one thing that's 100% certain, you're going to compromise the measurement accuracy if you put an adapter on and you don't have the correct calibration kit to calibrate after the adapter. So it's inevitable that's going to happen. So that makes the adapter quality very important. And you'll see that when we get to the measurements. So how badly the accuracy is impacted by this quality of the adapter is pretty much directly related to what you're going to get in terms of measurement performance and quality. A good adapter will introduce minimal error. And for the people of this particular category, the cellular industry, these MOPs, they lay out procedures and they basically have limit lines for several of the measurements. So for the field technician, they're making these measurements, and what they want is those responses to be below the limit line. Let's say if it's a return loss measurement, that response needs to be below the limit line. And as long as it's below the limit line, then it's kind of considered a valid measurement, and it will go into a closeout report, and they should get paid by the carrier, once the job is done. Now, sometimes you'll have an issue, and this is pretty standard procedure. If you're on a site and you're doing a system return loss measurement and you've got horrible return loss, normally the next thing you should do is start doing a distance to fault measurement, because there's clearly a fault somewhere in that system. And so distance to fault will help you try to locate where the fault is. And the fault can be a lot of different things. It could be the cable got pinched, or it could be, we've seen bullet holes through cables in remote base station sites. There's a lot of different things that can happen. Connectors weren't tightened properly, or water ingress, or, the list goes on and on and on. So this might be a little bit of an eye chart, and I apologize if it is. There's some text in here that's a little bit small, but these are examples of connectors or adapters that you should try to avoid. And so if you just do a Google search and you look for, adapters, you're going to find the classic sites, eBay, Amazon, and several others. And they're going to have adapters at really ridiculously cheap prices. The adapter on the left, $2.97 for an N female to N female adapter. And the adapter on the right is, I think that adapter was $8 and change. I don't remember exactly what the price was. But the key here is none of these adapters, and I'll show a different one on the next page, none of these adapters actually specify the VSWR performance of the adapter. So that should be a big red flag. When you're looking for adapters, and it doesn't have to be N female to N female, it could be any type, right? So N to 4.3 or N to 7/16 to N, whatever the conversion is, the adapter itself should have a VSWR spec. And if the company that's producing the adapter is building a quality product, they will be proud to put that VSWR spec on there, because they've manufactured that adapter with the highest quality possible. When you see these types of ads and very vague descriptions and very vague specs, I would run in the opposite direction. And you'll see why when I show you the measurements. So this one looked more interesting because it seemed to have a lot more specification to it. It had a defined frequency range, it had maximum voltages on it, it had a torque rating, they talked a little bit about the material, the nickel-plated brass, which is not really ideal, but for a lower-cost adapter, it might be okay. Gold-plated brass for the center pin. They even defined what the insulator was, so it's good. But again, sorely lacking the VSWR spec. So that would be a red flag for me. And so let's get into some measurements. This is the part that I think is the meat on the bone. So the device under test here was a simple 30-foot cable, or for those that are metric, it was like 9.1 meters, 9.2 meters. And just a cable to go from a radio head to an antenna. And the MOP defines testing the return loss of the cable, terminated with a load at the end of the cable, and set the return loss limit to 25 dB as we've done here. And what I had to do to make a connection to this particular cable was I had to use an N female to N female adapter, because the instrument that I was using has an N male adapter on it natively, and I couldn't make the connection to the cable. So I took a good quality adapter, connected it to the site master, and made this measurement. And, you know, so far, great. Results are great. This is the exact same measurement. The only difference adapter, and I used the poor quality adapter that we purchased. And the poor quality adapter looks great, nice and shiny, you know, it looks like a perfectly fine adapter. But when I connected that adapter, I completely blew my response up. And so the first thing that I would do as a field technician, if I measured this, I would say, hey, something's wrong here, you know, so I would probably start going into diagnostic mode and start doing some distant default measurements, which would lead me nowhere because there is no actual fault in this particular system. The fault is with that adapter. Now, if you remember earlier, I talked about the ideal scenario is to do a calibration after you've added the adapter. So here's the exact same measurement with the poor quality adapter, but what I did was, after I added the adapter, I did a calibration at the end of the adapter. So that removes or corrects the error caused by this adapter. And this is where the magic of vector error correction comes in, because you're able to do that. So I'm just going to go back for a second. This is before the calibration, and this is after the calibration. And if I go back 2 slides, this was the response that we had just adding the high quality adapter, but there was no calibration performed after the adapter was added. So if you compare this response to this response, you can see how close they are, which basically is reflecting what I had said earlier, that a high quality adapter will have a minimal impact on the overall measurement accuracy. And that's what you want. Okay, so this one here might be a little bit of an eye chart. If you look really, really carefully, you'll see there's 2 traces here, and I understand that my mouse, people can't see the mouse, but if you look at the trace, you're going to see a yellow trace, and you're going to see a fuchsia or magenta colored trace, and they almost lie one on top of the other. So basically what this is I believe the magenta trace was the measurement with the poor adapter, but after it was calibrated, whereas the yellow trace is the measurement without the calibration, but using the good adapter. So I just wanted to put this up so you could see how minimal the impact of the good quality adapter is without a cal versus what a real measurement would be if you actually did the cal after the adapter. So how does that impact distant default measurements? Because that's another common measurement that needs to be made. So basically now we're doing a distant default measurement on the same device, same cable, and with the good quality adapter, but without performing that second cal, we get an excellent response. So I've got my 0 dB response because I have a short and I'll terminate it at the end of that cable. I've got a good response at the launch area. So the launch area is at the very beginning on the left-hand side. That's where the cable antenna analyzer connects to the device under test. And the big peak at the far right is where the short is at the end of the cable. So perfect response, even though I'm using an adapter and I did not calibrate after the adapter. Now, what does it look like if I use the poor adapter? It should be obvious here. There's a couple of things to look at. First is the big hump at the very beginning of the trace. So that large hump is basically the effect of that poor quality adapter. You're kind of measuring the poor quality adapter in this measurement to some degree. And it has thrown off the distance default in that region horrifically. And distance default is one of these things that when there's a large fault in a system, the information shortly after that fault is not reliable. So you can say, I would say probably 1/3, the first 1/3 of this whole suite is not reliable data at all. When you get to the end where the short is, you'll see that it no longer reaches the very top of the graph. It's because there's some loss through that adapter that hasn't been compensated for because we did not do a calibration at the end of the adapter after we added it. Now, here's the exact same poor quality adapter, but we went ahead and did that calibration, and we've resolved the issues, you know, with no issues. You know, I mean, I have no problem with this measurement at all. The peak at the very beginning is slightly higher than it was with the high quality adapter, but not enough to be concerned. And then the other thing to look at, when I'll go back and forth between these two again, in the center, you'll see two humps that are slightly higher, like two peaks that are slightly higher. If I look at with the bad adapter, you see how those peaks don't look the same anymore. They're badly distorted. They're distorted because of that initial hump at the beginning. When I use now the corrected, after I've done the calibration at the end of the bad adapter, then I got that response. This response is nearly identical. So this response here and this response here are nearly identical. And one of them is the good quality adapter without the cal. The other one is the bad adapter, but after the cal. So I decided that since that bad adapter had such negative impact on the measurement, I mean, it literally throws a passing measurement into a fail, that I figured let's measure the VSWR and see where it's at in that frequency range, which happens to be PCS band for this example. So that bad adapter, the VSWR, is 2.02. So again, this is why these people don't want to spec VSWR with their poor quality adapters, because anybody that's intelligent, if they see numbers that high for VSWR, they would know not to buy that adapter. But if there's no spec on it, then you kind of make an assumption that it's going to work well. In contrast, I measured the VSWR in the same frequency range of the good quality adapter, and it's at 1.01. So that's almost perfect. You couldn't ask for much better than 1.01. So that adapter, the poor quality adapter, was actually purchased through a site that caters to the ham radio market, which they don't work at the cellular frequencies. They're usually working at much lower frequencies. So I decided to see what kind of impact that adapter would have at lower frequencies. Same cable, same measurements that we just saw the first time, except that instead of going from 1850 to 1990 megahertz, for these measurements, we'll go 50 to 150. And so here's the measurement with the good quality adapter added after, but not calibrated. Here's the same measurement with the poor quality adapter added, but not calibrated. And there's a certain shape of this measurement that I'm going to touch base on in a second. But this measurement still passed. So technically, a technician in the field could save this measurement and could submit it, and it would probably be accepted. But in reality, I mean, it's clearly not optimal. So I measured the VSWR in this frequency range of the poor quality adapter. And this is what I want to go to point out. You'll notice the slope of the VSWR is increasing with frequency. That means that the adapter is getting worse as the frequency is going up. Notice there's a slope in this measurement using that adapter, and there's a relationship between the slopes. It's not quite as steep, but you can see the upward slope. And that's basically showing you that as the VSWR is getting worse in the adapter, it's pushing your measurement higher and higher and higher. It's making your measurement worse, and it actually has a slope shape to it. We'll see that again on a different slide. So after not being very happy with the quality of the adapter in the 50 megahertz to 150 megahertz range, I decided to drop even lower. So this is still, ham radio guys, CB radio, 27 megahertz. I'm not a CB person, so I don't know all the frequencies there, but so I figured let's try it, let's see what happens. So there's 10 to 50 with the good adapter. There's 10 to 50 with the poor adapter, and notice that slope is there. And again, this is 10 to 50 with the poor adapter, but I've calibrated. So this looks a lot more like this one, which is the good adapter, but not caled. This is the poor adapter, but I did a cal. Just notice that the slope went away after the cal. So again, that's the magic of the vector error correction, which is part of the calibration process. This is an overlay of the two measurements. The yellow trace is the poor adapter with the calibration applied after the adapter was added, and the magenta trace is the measurement that was made with the good quality adapter, but no calibration. So you can see some variation there, but I mean, they're very, very close, and they're well below the limit. So I would say, the good quality adapter did not really impact the measurement enough to be of a concern. And again, there's that slope. This is the VSWR of the poor quality adapter in the 10 megahertz to 50 megahertz range. And the value is 1.03, which is a lot better than it was at the higher frequency. If you remember the higher frequency, it was at 2.02. So at this lower frequency range, it goes as high as 1.03, which isn't bad, but still pretty high compared to the good quality adapter, which measured at like 1.01. So I took this measurement because really an N-type connector is supposed to be a precision connector, and typically they are good to 18 gigahertz. So a very good quality N connector is good to 18 gigahertz. It has full traceability to national standards to 18 gigahertz, you know, if it's coming from a reputable supplier. So I decided to measure the adapters, the good one and the poor one, all the way to 18 gigahertz. I had to use a different instrument. This instrument supports frequency ranges all the way up to 40, but I'm only going to 18 in this case. So the worst case VSWR on the good quality adapter came in at 1.06, which is very respectable. Here's the poor quality adapter. It looks like, you know, a couple of mountains, or it's certainly a train wreck. I mean, a peak VSWR 10.69. It's a miracle, to be honest, that the vector error correction can actually calibrate this out. But what happens when you have really bad VSWR, like really poor quality adapters, you'll do a calibration, and that will take care of most of this issue. But that calibration will not be stable after that. The calibration will start drifting very rapidly because there's so much vector error correction being applied to try to fix this horrible response of this adapter that it's going to make your calibration unstable, and you'll have to recalibrate the instrument often if you're using these poor quality adapters. So as I mentioned, that adapter was purchased through a website that caters mainly to the ham radio market, and it was cheap. I mean, delivered was $21.64, and I think the delivery was actually more expensive than the adapter itself. I don't remember the exact breakdown between delivery and adapter, but it was cheap. The good quality adapter is our own 34NF-NF50A. It's fully specified, of course, to 18 gigahertz, and our specification for it is 1.1. So anytime you'll see a VSWR specification on an adapter, that's typically the maximum, and typically that will be at the higher frequency range. Now, in my case, when I measured it, the 1.06 was the peak, but it wasn't at the full 18 gigahertz. It actually went back down a little bit, so there was just that tiny little hump. But anyways, I mean, spec was 1.1, we measured 1.06, so it's performing to spec or slightly better than spec. But it's not $21.64. Ours is $470. But even still, if you compare that to how much it costs to roll a truck to a site, you know, the takeaway here is that you're going to go through all the effort. You're going to send your crew to that site, and you're going to give them those tools to do those measurements. If you load them up with cheap adapters because, you know, you think you're saving some money, you're not really saving any money, because those cheap adapters are going to come back and they're going to haunt you. They're going to cause you a lot more grief than what it's worth. So, you know, it's worth spending the time to invest in high quality adapters. And there are several companies supplying the cellular industry with high quality adapters. You don't have to go to a test and measurement company and buy a metrology grade type adapter like the Anritsu adapter. You can buy adapters from companies that cater to the cellular industry for probably a price that's going to land somewhere between $21.64 and $470, and still get a fairly decent adapter. Just keep your eye close on the VSWR spec. That's what you want to look for. So now you have adapters, they're in your kit. You really don't know what the VSWR spec is because you didn't buy them. They're part of your kit. Can you test them? And the answer is yes, you can. And you can actually test them in the field if you've got the right equipment. You need a working cable antenna analyzer or vector network analyzer. You need a calibration kit that allows you to calibrate the analyzer at the connector where the adapter will connect. So in my case, I had an N female to N female adapter, and I had an N male port on my cable antenna analyzer. So I needed an N female cal kit so I could calibrate my cable antenna analyzer. Instead of talking about it, I'll just show it to you. So here we go. So for the N female to N female, this is basically I calibrated it using an end-female calibration kit. I connected the adapter to the analyzer. The calibration, and you can't see my mouse, but that arrow is pointing to where the calibration is done. So the calibration is done there before the adapter's added. Then you're going to terminate the end of the adapter with a precision termination. And a precision termination could be the load that's part of your calibration kit, as long as it's the right gender that it mates to the adapter, or you can buy precision terminations separately. And what you're looking for in a precision termination is they're most likely going to be spec'd in return loss. So if you're in the 42, 40, I would say probably not less than 36, at the very minimum, 36 dB return loss on that termination. But the higher the return loss is, the better the results are going to be. Just like the adapter affects your measurement accuracy, your termination can affect your measurement accuracy of the adapter itself. So if you don't use a high quality termination, you won't get a high quality measurement on the adapter. I hope that makes sense. So now that you've done that, of course, you can measure the VSWR or the return loss of the adapter. It's your choice, and it's just a selection on the instrument GUI. And then I'll go through these next few slides fairly quickly because it's basically the same process. The only difference that changes is now this is an end male to end male adapter. So you need to make sure that you can, at that point, you need an end female connection or an calibrated end female test port. However that's done, whether it's made of end female on the instrument itself or whether you put an adapter to convert your test port to an end female. Then you'll use end male calibration components. You'll do your calibration like you did before, and you'll connect, and then you'll terminate with an end male on the other end or an end female at the other end, depending on your gender of adapter. And the same rules apply if it's an end to a 4310. So in this case, you need end calibration kit to calibrate the cable and analyzer, and you need a 4310 precision termination to place at the end of the adapter. And male and female, 4310 male, 4310 female. So the genders are what's important here. As long as you've got the right types of components, you can calibrate and you can test those adapters in the field without any issues. So why do they go bad sometimes? So you had a good adapter and now it's gone bad. So there's a lot of different reasons. I can't go over all of them. I'm going to say one of the common ones is the way people treat the adapters. I mean, I've seen people basically just toss them into a box. You know, there's 25 adapters in the box and they're done and they just toss them in. They don't give any second thought to it. That's probably not a good way to treat your adapters. So that's one thing. The quality itself of the adapter, I talked a little bit about, nickel plated brass as opposed to stainless steel or gold plating on the center conductor. That gold plating on the center conductor can be thick or thin, depends on who's manufacturing it. And if it's a $8 or $9 adapter, you can bet it's an extremely thin gold plating and it's going to be worn off probably after the first 5 or 10 uses. And then how well was it cared for? Was it kept clean? Was it mishandled? Was it dropped? You're out in the field, you drop it in the mud, you pick it up, you blow the mud out of it. That's probably not going to help the life of your adapter, and it's not going to help you when you're trying to get some decent measurements. And then how you connect it. So there are people that, this is a bad habit, and I see a lot of people do it, even in my industry. They turn the whole body of the adapter when they're screwing it on to the instrument. And when you're doing that, what you're doing is you're turning the whole center conductor. One pin is turning against the other pin. So you've got a male pin and a female pin, and those two are rotating against each other. So you're wearing out that gold plating on both pins, when really what you should be doing is you hold the body of the adapter stable and you just turn the outer portion. So the nut on the end connector, for example, that's what you want to turn. Hold the body, turn the nut, and that basically slides the pin into the female in a straight motion without twisting. It boggles my mind how many people I see that spin the whole adapter. So you want to avoid doing that. The other thing you want to be careful of is excessive force. I've seen people take adjustable wrenches on sites and they start torquing these things and they have no idea how much they're torquing them. And if you over torque an adapter, you can almost guarantee you're going to cause physical damage to it. And once that happens, that performance of that adapter is just going to drop off the cliff. So there's lots of different things that can happen. And this is not all the things that can cause them to go bad, but these are probably the more common things. So I hope there was a lot in here. I hope that you guys got some good nuggets, if you want to call it that, from this. And I appreciate the time that you spent. And so we'll do some questions in a few minutes. All the theory and everything in here, as I mentioned earlier, it applies to higher frequency measurements. So if you're working in a lab with a benchtop vector network analyzer and you're sweeping up to 40 gigahertz, well, guess what? If you have to put an adapter on and you can't calibrate it to any of the adapter, the quality of that adapter becomes even more critical. Now, vector network analyzers have some additional features that you won't find in most cable antenna analyzers. They have a feature called Deembedding. And Deembedding, I don't know if I listed in here. Yes, here it is here. So Deembedding is the ability to remove the effect of the adapter that's been added after calibration, but it requires an S2P file. So it requires somebody to have measured that adapter very carefully and precisely and saving an S2P file of that adapter. So now you can add the adapter to the port or to the end of whatever, your vector network analyzer, and then you go into your de-embedding menu and you de-embed the adapter, which is basically loading the S2P file in there. And the analyzer itself will mathematically remove the effect of the adapter. But this is not available for people in the field, you know, the cellular industry and the cable antenna analyzers. They don't have these features. Oh, there we go. Let me go back. So now we've got some questions.
Presentation, it was very interesting seeing the effects of the adapters and the calibration. A couple of questions. For example, let's start with how long is a calibration valid and when do you have to recalibrate other than when you add a adapter? Do you have, I guess, put another way, does a calibration remain valid as long as you have the same adapter attached to your instrument, or can it go out of calibration even if you don't change adapters?
So that's an excellent question, Martin. A calibration can remain valid for a long period of time, and I'll say, I don't want to use the word indefinitely. It depends on how stable the cable antenna analyzer or vector network analyzer is, but it also depends on the ambient temperature. So when we do calibrations on our products, whether it's a cable antenna analyzer or a vector network analyzer, at the moment calibration is performed, we are capturing temperatures inside the instrument, and that becomes part of the calibration data. And so we characterize our products across a certain temperature range. So from the calibration temperature, we can usually accommodate a drift of ambient temperature. It depends on the models. Some of our models can support up to plus or minus 20 degrees Celsius without having to recalibrate. Other models, it's plus or minus 10 degrees Celsius. Obviously, the higher in frequency you go, the smaller that window is. But for the cable antenna analyzers, plus or minus 20, plus or minus 15 degrees Celsius. But the key is the instrument constantly monitors that in the background as you're making measurements. So on the SiteMaster products, if by chance, you know, let's say you calibrated in the truck because it's cold outside, so you got in the truck and you did a calibration real quick, and then you get outside and you start taking measurements and the temperature starts getting cold, the analyzer will actually alert you and it'll pop up a message to tell you, hey, your calibration's not valid any longer, and then you can actually do a new calibration at that different temperature, and it will hold that until the temperature changes by a certain amount.
I see. Can you explain what you meant by a calibration plane? Can you explain what that means?
So the calibration plane is what's basically defined during the calibration process. And the calibration reference plane, we call it a lot of times we call it the reference plane. It's dependent to some degree on the connector type. And so I can say for, let's say, the end male connector type, if you look at the pin on the end male, after the calibration's been done, the reference plane is at the tip of that center pin. And so if it's an end female, then basically the center pin accepts the male pin The male pin goes into the female a certain amount, and that amount of where the male pin goes into the female pin, that amount is where the reference plane becomes for the end female.
So if you were to attach a adapter and then a cable, and then put your short, open, and load, which you get in your calibration kit, put that at the end of the cable if you can. You may not be practically able to do that, but if you could, that would take into account the cable and the adapter as well?
Absolutely, absolutely. So you could have, let's say you have a 4310 test port cable. So it's got 4310 on each side as opposed to N on each side. And you've got an N-type instrument. So you can put an N to 4310 adapter on the instrument, connect the cable to the 4310 adapter on the instrument, and then at the end of the cable, using a 4310 calibration kit, you can perform an open short load, and the effects of that adapter and cable will be corrected out by the calibration process.
I see. You also mentioned that if you apply too much torque to an adapter or to any connector, that you can damage it. How do you know if you've applied too much torque? Is there any way to know that?
That is an excellent question. So I'll talk about a metrology lab environment first. So I shouldn't say almost, every connector type has a specified torque rating. And there are torque wrenches that are made specifically to address that. So, I'll take a K type, which is an Anritsu connector. It's a 2.92 millimeter. I believe it's 8 inch-pounds is the torque rating. So you can buy a torque wrench that it essentially will only allow you to torque that connector to 8 inch-pounds and not more than that. Now, if I go take a cellular example of a 716 DIN connector, which is the large connector that goes on the Helix type cable, the torque, I don't know off the top of my head what the torque rating is for those, but they do have torque wrenches, and the torque wrenches are made to basically allow the tech to only torque that connector to the amount of torque specified. So yes, you need a torque wrench if you want to properly torque connectors, and you'll see, I'm sure most people that are probably still listening to this, if they work in the cellular industry, when they're doing their N calibration, they're probably not using an N-type torque wrench. N is interesting in the sense that some N connectors have the flats on them so that you can actually put a torque wrench on them, whereas some N connectors don't. They just have a knurled grip on them. So how do you put a torque wrench on an N connector with a knurled grip? So there's some gray area there, but in general, for metrology lab grade measurements, there's virtually a torque wrench available for any type of connector that you're using. In the field, for sure, with the 716s DIN connectors, there are torque wrenches available. There are torque wrenches available for N if your N is lucky enough to have the flats on it that will allow you to connect a torque wrench to it.
Okay, Philip, thank you so much for your presentation and for your question answers. And thank you again to Anritsu for sponsoring this session. For EE World, I'm Martin Rowe. Thank you for watching.